Hey everybody, this is MAT 221. This is Mrs. Johnson. This is Calculus 1, Section 2.8. We're talking about how the derivative and the second derivative and the original function are related to each other. After doing our analysis, notice we can sketch our derivative graph, and notice that where the original curve was rising, the derivative was above the x-axis. Where there was a horizontal tangent line, there's a 0 on the derivative curve. Where the original curve is decreasing, the derivative curve is below the x-axis, negative values. Where I have a horizontal tangent line, I have a 0. Notice at the point of inflection, I have the most negative value there on my derivative. From here on this interval where the original curve was rising, or increasing, notice the derivative curve is above the x-axis. Notice that the point of inflection is where it was of the green graph is the highest point on my derivative graph. Notice when I have a horizontal tangent line, I have a 0 on my derivative graph. When the original curve f of x is decreasing, the derivative curve is below the x-axis. At the point of inflection, my derivative curve is the lowest value. Notice when I have my f of x function has a horizontal tangent line, I have a 0 of my derivative. When the original function f of x is increasing, notice the derivative curve is above the x-axis. Notice at the point of inflection, the derivative is the highest value. Notice when I have a horizontal tangent line of my original function, my derivative function has a 0. And notice when the original curve f of x is decreasing, the derivative curve is below the x-axis. Now, if I were to sketch the second derivative here, now let's talk a little bit about antiderivatives. We've kind of done a little bit about this in our earlier exercise when we started with a derivative curve and then kind of sketched an original curve. This is called looking at an antiderivative. Now, we're going to not do this too much just yet, but I do want to just mention it here in section 2.8, that going backwards, if we're given an original curve, if we're given a derivative curve and we want to go backwards to an original curve, we take what's called the antiderivative. So in many problems in math and its applications, we're given a function f and we're required to find a function capital F whose derivative is the given function f. Matter of fact, Leibniz and Newton, that's actually when they started calculus, that's what they started looking at. They started looking at rates of change curves first and then started going backward to the original curve. So if such a function, capital F, exists, we call it the antiderivative of f. In other words, an antiderivative of a function, capital F, is such that the derivative of capital F will give you this function. In other words, this is the derivative of some other function that we call capital F. Let capital F be the antiderivative of the function whose graph is shown. We can now answer questions about the antiderivative function, or in other words, the function that this function that we're looking at is the derivative of. Where is capital F increasing? Well, capital F will increase wherever the derivative curve, which is the little f, is positive. Well, wait a minute. This curve, little f, is positive everywhere. So since f is the antiderivative of f, we have that the derivative of the big curve, capital F, is given by this curve. F prime is positive where x is greater than 0. This means f is increasing on the interval from 0 to infinity. Capital F is increasing from 0 to infinity. This is another way that we're looking at a derivative function. It doesn't say derivative, but it's telling us that this is a derivative of some function we can't see. Where is the capital F function concave upward or concave downward? Well, the original function, capital F, will be concave up or concave down when the second derivative is either positive or negative. In other words, we're the derivative of this curve. So F is concave upward when the second derivative of capital F, which is the derivative of this curve I'm looking at, is increasing. So we can say from 0 to 1 and from 3 to infinity, little f, which is a derivative curve, is increasing. If the derivative of capital F is increasing on those intervals, then we know that that's where capital F must be concave upward. Similarly, capital F will be concave downward when the second derivative of capital F, which again, remember, we can't see capital F, we can only look at its derivative, which is little f, where little f is decreasing. This is on the interval from 1 to 3. At what values of x does f have a point of inflection? Capital F has a point of inflection. Again, capital F, we can't see that curve, but we know that this curve, little f, is the derivative of capital F. And we know inflection points are going to be at the peaks and valleys of the derivative. Remember, it was the most positive or the most negative. So capital F has an inflection point when the concavity of F changes. And from part B, we know that capital F changes concavity at x equals 1 and at x equals 3. Now, this looks very different. We're not asking for the inflection point of this graph that we're looking at. We're asking for the inflection point of the graph I can't see. But this is a derivative graph, and we know that it will reach its peaks and valleys at inflection points of capital F. If capital F of 0 equals 1, try to sketch a graph of this function. Well, what did we say? We said that the function capital F is increasing throughout because the derivative curve, little f, is always positive. We know that we're increasing and concave up till about 1. We're increasing and concave down till about 3. And then we're increasing and concave up again. How many antiderivatives does f have? Actually, a whole bunch, infinitely many. Each one of them will look alike. They'll all have that same general shape, but I could just shift it. Notice the first one said we started at a given point 0, 1, but we could start at 0, 1/2. We could start at 0, 1.5. We could start at 0, 2.25. And notice the graphs will all have the same general shape. All of these functions will have little f as its derivative. So the members of the family of antiderivatives is many, many different graphs, infinitely many graphs, all looking like that same general shape. All right, that concludes section 2.8. Now, antiderivatives is a very difficult topic that we're just skimming the surface on right now. We'll hit this again later in the course. But the predominant thing that I'd like you to do for section 2.8 is to make sure you understand the relationship between the original function, the derivative function, and the second derivative function. I'll be adding some more videos with some worksheets in the next day or two. Have a great day.